Okay.
Therefore, you assume that what the time it is, it's 5 o'clock, they're going to close it. Therefore,
Okay,
you
I
make
get
sure
it.
you do everything before that time, because they cannot arrange for each individual. Therefore, some of you are doing fast, probably will finish after 2 hours and a half. Some of you are a little bit slower, 2 hours, 50 minutes. Some of you are like slow like me, you will be the last one. Therefore, make sure that you do it on time, that you don't end up with any problem.
Okay, thank you.
Because again, it's very, very unfortunately, it's not easy time for you, and it's not easy time for them.
Yeah,
Okay,
they didn't give us any instruction about that.
I will ask them. I will email you whatever information I got from them. Again, this is the same as midterm. It's nothing special. But I just received 125 email this morning. I will go through them, and if whatever is related to you, I will send it to all of you. Please read it, prepare yourself, and arrange. Leave 10 minutes at the end, as soon as the 2 hours 50 minutes exam.
Okay,
Leave
thank
10
you,
minutes
sir.
at the end that you can upload whatever information they're asking you. Okay.
Okay.
This is again is I know it's not easy for you. It's not easy for them. And but the question, we're trying to compromise to have some evaluation. That's all we're trying to do.
Sir, I have a question about, so we were given a practice exam just to make sure the system worked. Could you ask or maybe provide us an email of someone we could contact to get access to that practice exam again? Because it was really helpful to like see if there's any bugs or anything like that.
Again, what I can do, I can forward you all the information I get from them. And on that one, they give you the same thing I sent it before, midterm exam. They're giving you the procedure and they're telling you where you should go and what you do, okay? Again, I'm really naive. I do not know how the system works, and I do not want to know it. But you read it, all the email, follow the procedure. But based on feedback you give it to me, I communicated with them, and they trying to solve the issue, the problem that you had in midterm. Some of you because of special attention that you needed, and some of you because of noise and so on. Therefore, they promised me to solve this problem, and they are going to contact those students they need special help. And also for the rest, they are trying to make them, they have trained all the invigilator, and they ask them be quiet during the exam. And if they need to talk to a specific student, put them in a separate room and solve the problem there, not shouting, screaming, and so on. But again, at the same time, you have to cooperate, all of you, because what a mistake, any issue comes out, then unfortunately at this time, all of you have to pay the price for that. Because of the system, I do not know. Again, I provided, I don't know, 5 questions, 6 questions, 7 questions, no, I do not know, 10 questions, 20 questions, anyway. Manage your time. Manage your time, and each probably question, some of them is only a few lines, some of them probably more line, okay? Calculation you have to do it. The only thing you have to do here, I believe most of you have a problem managing your time and trying to put a straightforward, clear. You write x equal 5 now at the beginning of the page, and when the end of the page you are going to use x equal 5, that 5 become 15. Pay attention. 6 plus 4 become 10. Some of you do not know, you are in rush or something, you write 6 plus 4 become 11. I do not know. Because look at your midterm paper and you see there are a lot of ridiculous mistake, okay? Pay attention, but the good thing, I like it and I enjoy it, now is clean because you have to write it right on the page, and you don't go from page 1 to page 16 and come back to page 5 and go page 10. No, you have to put them in one page. That's good thing that I enjoy it. But the rest is in your shoulder. You have to manage your time. The question is easy. I cannot say easy or difficult because I'm preparing the question, but read it, understand the question, and answer the question. Look at this problem. Let's do it together. Find out what information is given to you. Please write it down in your paper to see your mistake. We have this half cylinder, the diameter is given, the temperature of these two surfaces is given. He's asking you to determine the drawing rate per unit length. We assume the L is equal to 1, okay? How you are going to do that? What that means, the drawing rate. What that means. Any suggestion? Look at here, it's just some questions, blah, 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 blah. Here it mentions occupied with water soaked material to be dried. Okay. Therefore, in order to dry, what will happen? There is an energy exchange between these two surfaces. Therefore, read the question, though, and he mentioned long semi-cylindrical. Why he mentioned long? Why is mentioned long, not short? Because he's trying to make an assumption. The energy losses from the end are negligible to the length, okay? That's they're trying to mention, okay? It mentioned long, it means there is only these two surfaces, they see each other all the time. That's all. There's nothing else. Therefore, there is only what energy goes from 2 goes to 1 and 2. And whatever goes from 1 goes to 2. Therefore, here, the only thing is asking you to calculate net energy exchange between these two surfaces. That's unknown. Please write it down and try to see how far you can go. Any suggestion, ladies and gentlemen? Hello? Any suggestion?
We could find the amount of energy emitted from the surfaces?
Yes, there are these two surfaces, and to consider the one cover the other one. Therefore, there is only energy exchange between surface 1 and 2. There is no other body involved. That's why he mentioned is long. Therefore, this cylinder is long. Therefore, we can ignore energy losses from the end. And the only we can write a reciprocity rule, A1 F12 to A2 F2 to 1. Now, what is the shear factor of 1 to 2?
Would it be 1?
Are you sure?
No.
Yes, you should be sure.
Yeah, I'm sure.
Because whatever emitted from surface 1 eventually will be captured by surface 2. Look at the picture. Because this is flat, if you write the summation rule, okay, let's forget about it. Let's write summation rule for surface 1 is F11 plus F12 is equal 1. Do you agree with me?
Yeah.
Okay. Therefore, if you ignore the losses from the end, there is only two surfaces, 1 and 2. Therefore, I'm going to write the summation law for surface 1. It mentioned F1 to 2, F1 to 1 plus F1 to 2 is equal 1. Now, surface 1 is a flat. Can it see himself?
Nope.
Fantastic. Therefore, F11 is equal 0. Therefore, from here, you can find F1 to 2 is equal 1. Therefore, now you find shear factor from 1 to 2. You can calculate, you can use a reciprocity rule if you want to calculate from 2 to 1, but you already found from 1 to 2. Now you would like to calculate the net energy exchange between 1 and 2. Between 1 and 2. Write the equation FA1, F12 times sigma, the temperature difference. You can calculate the net energy exchange. You have talking about 1,000, and they are talking here. Therefore, now you can find the net energy exchange between this surface. Okay, the net energy exchange is watt per second. Joule per second is watt. Now, this amount of energy has been exchanged, but now there is some material there is wet. We mentioned water salt. It means it's wet. Now, when it's there, when energy exchange, some of this water will be evaporated. It's trying to find at what rate those materials are dry. Okay, read the problem, look at the problem to see what exactly is given, what exactly wants. Let's go back to the solution. Again, here 1 to 2, the temperature is 1,000, and the other temperature is 370. The U factor can be determined from this one. Look at surface 2. If you have any question, ask me, please. Is this correct?
Yes.
Yeah, because again, the only time is correct, please, my friend, you're right. The only time is correct if he assumes this is long. If it's short, we cannot assume because there is some opening at the end here. There is one surface here and one surface there. There is a surface here is 3 at the end and the 3 at the end here. You have to consider that one too. But here we assume is long, therefore the contribution of this surface at the end here and the contribution of this surface at the end here is negligible. That's why they use word long here, okay? Long. That's why I mentioned we can ignore contribution of this surface here and contribution that surface at the end, okay? That's the only thing we can do it because we mentioned it's long. We can make that assumption those contribution is almost negligible. Otherwise, you have another one, 1 to 3 here and 1 to 4, okay? But here. And then since we can, since one is flat, it cannot see energy emitted from itself. Therefore, this term is equal to 0. Because whatever energy emitted from surface 1 will not be captured by surface 1. That's the meaning. Energy emitted by surface 1 will not be captured by surface 1. That's the meaning, okay? Therefore, now we have this one. Therefore, now we can write reciprocity rule. We can find F221, whatever you would like, okay? Now we find the shape factor. Now the question here is how much energy is exchanged? It's easy. Again, you can write the amount of energy exchange from 2 to 1. You don't have to calculate here. You can write also the term in the energy 1 to 2. Okay, it doesn't matter. 2 to 1 is the same amount of energy used to evaporate those water from the material. And as you know that, this is called the mass of the material times the heat of evaporation that we have here. Change from liquid to vapor, okay? Therefore here we can calculate here. Again, as I mentioned, here you can write A1, F1 to 2. You don't need to do that because we have reciprocity rule. This times this is equal to this times this, okay? You don't even need to do this calculation. You can write A1, F1 to 2, okay? Because these two are equal. And this we write it down, and this mentioned pi L, D is the area, that times that, okay? Therefore, you can write that equation mentioned F1 to 2, and area is D times L, okay? Okay, therefore now you can calculate because you have the temperature of T1, you have the temperature of T2, you have shape factor, you have all this information. The only time is this guy is missing, that you can find it from table 5.2 in your building science or from your heat transfer textbook. Okay, therefore this number can be easily found that you have, okay? The rest you just plug number, and it mentioned per unit of the length. Remember again, the length was not given. It mentioned dry rate per unit of length. That's why we have here this one. Okay. Again, this is one of the assignment. I did it here, but you have already, I'm going to send you the solution because this was part of your assignment. I just want to explain to you what exactly. Any question, ladies and gentlemen? Again, read the problem. You know all the information, but now you have to show it. Okay? Therefore, you have to read the problem, understand what exactly is given, what assumption that you can make, and then put the procedure. Do not do try and error. That's why I insist always do the problem right now in your paper, that you can see where you're making mistake. If you see it, you will not make that mistake for the rest of your life. Any question, ladies and gentlemen?
Can you show the question of the exercise again?
Yes. The problem come from your textbook. You should have your textbook, sir.
Okay, I do.
Oh, is it 1343? Okay. Any question? 1, 2, 3. Let's go to the next one. Anyway, I'm going to send you the solution, this one, because this was part of your assignment. Okay, let's look at this one. Read it carefully and try to do it. Let me take my time here. I go for a walk. I will come back in 10 minutes. Okay.
Sir, I think you muted yourself.
Yes, sir, you want to hear me? Okay, good. We have a dam. Here, solar radiation comes at the surface, the value is given. This side exposed to convective heat transfer by water, the H and T infinity is given. This surface is insulated. Therefore, we're trying to find the temperature 1, 3, and 6. Since each of them will link to the other temperature, therefore we have to write 6 equations, right? The whole idea of this exercise here, trying to write equation for each node, 1, 2, 3, 4, 5, okay? Did you write the
Excuse
equation
me,
for
sir?
number? Yes, dear.
I had a question for number 1 for the convection area from the air where like the radiation is coming from. Do we have to measure like the triangle area?
That's a good question. Look at here. You can assume here is this side, this part exposed is water, and this side is only radiation here.
Yeah, so like half of the diagonal between 1 and 3?
Yep.
1 to 3 is radiation.
But for the convection area?
Convection, there's no convection. You have
There's no convection from the air on the
No.
white side?
Okay.
So why is it saying that we have a 25-degree?
So louder a little bit, please, because we have a convection here. And
Yeah, I thought there was convection from water and the air.
Okay, there's a convection between water and the surface.
Yes.
Okay, this side you have some constant heat flux mentioned, right?
Yes.
We don't count the environment with the convection as well?
This is this side, this surface is you have constant heat solar radiation plus.
That's what we were saying.
So
That's what we were saying. We're asking. She was asking what the area that we're supposed to get. So you said half of the hypotenuse of the triangle, right?
yeah, okay, because if you draw the node here, this half of this belongs to water here, and this one between node 1 and node 3 half here is belong to this node. That you have some solar radiation plus some convective or radiative heat transfer on the surface. Did I answer the question?
Yes, thank you.
Good. Did you write the equation for node number 1?
Yes.
Good. What is the equation?
Well, it's a steady state and there's no heat generation, so those terms are 0. So it's basically just the sum of all the Q values for each type of heat transfer.
This part, what will be? You have conduction from here to here to material. Did you consider that part?
Yeah.
Then you have convection, and then you have conduction from here to here, and also some radiation and convection to there. Okay, let's see. Did you get this equation?
Yes, yes.
Does anybody have any question on this part?
Should we count the convection from above as well?
I mean, there's no convection to above here. There's no surface.
Oh yeah, true. Sorry, my bad.
Okay. And does anybody have a problem with this part? This is only referring to this length, because from here to here is 1 meter, from here to here is 1 meter, but this is a triangle. And in case you do not know what I'm talking about, let me go to this part, basic mathematics. Yeah, you have A, this is sine of the beta is equal A over B. You are trying to calculate the B, and you're trying to calculate the B, become A over sine of beta, okay? Okay, therefore that the sign that you have here is because we know this length is L over 2 in our case, and we have the angle here beta, and therefore we're trying to calculate what is the length here that exposed to solar radiation and convection, okay? Therefore that's typical. We have convection, conduction from here to here, and the way we have here, okay? Let's go to note number 2. The usual we have here, this. Could you please write the equation for note number 3? Okay, therefore I will show you all the equation because we need more time. And for note number 5, it's mentioned it is insulated. You can, to simplify, you can assume this is symmetric. The note here is also 3. Because it's insulated, it means dt over d is equal to 0, dy is equal to 0. It means there's a node here has the same temperature as 3. And this way you can consider this is an internal node, and you can easily calculate this plus this plus this plus this divided by 4. And that's exactly the point here, okay? And 2t here because we assume it's symmetric. And you're writing for node number 5. Here, node number 6 is the same. Again, we can write this one, okay? For practice, the idea here is be able to identify the element involved and write the equation.
Sorry, Professor.
Yes, sir.
Are we gonna have to solve this type of problem in a transient heat conduction in the final?
No.
Okay.
I'm not going to give you 5 equations. No, I'm trying to identify.
No. I mean for the transient one.
Transient?
The I plus 1, yeah.
If I ask you, I will ask you to bring your computer.
Okay, cool.
Anyway, you are sitting in front of the computer. I can do that. Therefore, if you do this one steady state, you get this answer. It's not the answer. Is not the question. The question was trying to identify how to solve. Okay. If I give you the example, probably maximum two unknown. Okay, that you can do it easily. Okay. Any question? Let me go to next one. Any question? Are you writing? Are you taking picture? Are you sleeping? Which one?
All of the above.
Good. The best one is to dream.
Sir?
Yes, sir.
For node 2, the first convective equation, should it be Ti minus T2?
I'm writing T2, right? This you're writing for T2. Yeah,
Yeah,
it mentioned, okay, this is, no, this type, yeah, this has, okay. Yes, this is two, right, okay, I understand.
okay.
Yes, because that's right. You are right, sir. You are right, sir.
Thank you.
Sir,
Yes, yeah.
is there not conduction from 3 to 1? Am I not seeing this right?
Can somebody answer this question? I do not know. She's asking if there's a conduction in this circuit on 1 to 2.
No.
Why no, why yes, why?
It's the same thing as if we take 0.5. We don't consider 0.2 affecting 0.5. We only consider 0.4 and 0.3. So in
Okay,
this case, we use.
Her point here, this is connected together.
Yes, it is. Same thing for 2 and 5. They're connected through the middle, yet we're not taking the effect of 0.2 to 0.5. We're taking 0.4 and 0.3, considering that those two are the acting 0.25.
Isn't it because of the assumption that it's two-dimensional?
Say it louder, please.
Isn't
It
it
is
because we
two-dimensional.
assume that it's two-dimensional, so it's only going from X and Y direction?
Are you happy with this answer, madam?
I'm not sure, but I just don't know.
No, it's good. I mean, the question, excellent question. Think about it, and if you need question, send me an email, okay? The idea here is trying to identify the parameter. His point here is we assume it's two-dimensional, therefore, but again, if I play devil advocate, these two are connected together from here to here, and there is some material going to it. The easiest way I'm going to visualize it, I can assume this is a rectangular like this here. Okay, if I put a note here, therefore I can mention this is a two-dimensional problem. Okay, it goes to here, and from here to here. In this case, we somehow consider that happened to 1 to 2. Okay, and here is mainly received solar radiation. Okay, again, look at the problem. If you have any question, please do ask me. Let me go to next question because we have 2 more questions left. Read this problem. Please don't rush to solve it. Do not rush to solve it. Find out what exactly is happening, okay? Identify what information is given to you. What is the procedure? What the end result is asking you. Is asking you to determine the rate of heat loss from the tank by convection and radiation. Again, as mentioned, we have a tank, the diameter is given, located in the bathroom or house, maintain that bathroom, that room is at 20 degrees and it's hanging from the ceiling, okay? I do not know why they have the vacuum sign from the ceiling, okay? Probably there's some information there, I do not know. The surface temperature of the tank is to be 44 degrees and the emissivity of the material is 0.4. And since this is inside the bathroom, we assume the temperature of the wall is also to be at 20 degrees. Again, here is, we give you another 10 minutes time to think about it and trying to do it. I give you 15 minutes. Please read it, do not rush. And trying to find how far you can go. I go for a walk. Any suggestion?
We need to calculate the Grashof number.
Okay. What is the characteristic length?
AS over P for a vertical cylinder.
The height of the cylinder.
The height of the cylinder. Therefore, first thing here is we have a cylinder. Therefore, it's hanging in the air. Okay. Therefore, there is some radiation, some natural convection from the length of the cylinder. Height. Okay. Cylinder. Therefore, there's a convection here. And it's hanging in the air. Therefore, there are some natural convection from the bottom, natural convection from the surface. Therefore, you have natural convection and forced convection from three surfaces: vertical, top, and bottom. Therefore, you have to analyze each of them separately and then add them up together. Therefore, look at the problem here. You have to write down first the diameter is 40 centimeter and the height is 110. We have R, D, and L. And we have the temperature of 44 for the surface, 20 degree for air, and the surrounding, and emissivity is 0.4. Okay? Let's do the problem together. Therefore, you have a cylinder right here, given the temperature is given, and HVAC is given. Now, first look at the length of the cylinder. Okay, the length is 1.1. But first, we have to calculate, we have to look at the table, A15, and find the physical property of the air, okay? Now, the temperature here is the average temperature. 20 degrees is the environment that we have, and temperature for surface is 44. We add them up together, become 64 divided by 2, become 32. And we can look at the physical property. Now, we identify the processes in natural convection. Therefore, we calculate the Grashof number. Let's look at which surface first. Let's look at the length of the surface, okay? Now, we calculate here, and the length is 1.1. We have the temperature difference of 44 minus 20. We have length is 1.1, and then we have physical property, and we calculate the Grashof number. Okay? Check if you, again, I remind you, please, this is characteristic length to power 3, Grashof number, kinematic viscosity to power 2. Keep in mind and make sure when you are doing it, always do not forget. And then become 10.88, 10 to power 9. Now, which correlation should I use? Now I need to go and calculate the Nusselt number. What should I do?
Should we get the Rayleigh number?
Pardon me? You multiply by.
Should we get the Rayleigh number multiplying by P Prandtl number?
Prandtl. Okay, we calculate Rayleigh number. Now, which correlation should I use? Yes, louder, please.
Yeah, I'm sorry, for vertical plate.
Right, therefore, I have to go back and look at the table 9.1, okay? Table 9.1.
Yeah.
9.1, we have a vertical cylinder. And mention vertical cylinder, if diameter is bigger than this, we can go, we assume it's a vertical plate. Therefore, we have to verify this is valid, okay? We have a Grashof number, we have length, and so on. We go back and calculate this value to make sure this condition is, then if it's correct, then we can go back and use it as a vertical plate. A vertical plate can be used as vertical plate when this condition, if this is bigger than this number. Now, if you look at here, we have in this range, we have in this range, and we have the entire range. Therefore, you can use this one for entire range, and you're not worried about this one, okay? Let's go back and verify this condition. We know the characteristic length, we have the Grashof number. and 2 power 1/4 and trying to verify it. Okay, therefore we verify it. This is the diameter that we had, and this is verify, and this number become 1.5. And I'm sure you agree with me, 1.5 is less than 0.4. Therefore, satisfy this condition, and we can assume it's a vertical plate. Therefore, we go up there and look at the vertical plate. We have the Prandtl number, we have a Grashof number, and we have that equation, and we try to find the Nusselt number. Could you please calculate? And if you calculate the Rayleigh number, you can see it's almost on the border between the two equations, 1 and 2.
Sir, I have a question.
Yes, sir.
What if we get the cylinder, but the diameter is smaller than the equation?
I will make sure that I give you that a problem that satisfies this requirement.
Okay.
This is from my side. If in reality, tomorrow you find the work, and that's also the case, you have to go to the library and look at handbook of heat transfer, and there is plenty of equation.
Okay.
Again, as I mentioned, in your textbook, they give you one equation as an example for each scenario. If you go to another textbook, you will see the equation is different from the ones given in your textbook. Okay, because they have a variety of correlation. Okay, satisfy here. Let's go to the next step. And here is your Rayleigh number. And if you look at the table 9.1, you will see it's in the border of the two equations that you have. Therefore, use the third one to satisfy the entire range. Okay, then you go, you have the Nusselt number, and the characteristic length is the L, and you have conductivity, and you can calculate the heat transfer coefficient. The heat transfer coefficient 4.0, right? It means your natural convection is 4 times higher than conduction. That's the meaning of Nusselt number. You have the H, you have the A. Now you can calculate the total energy exchange. As I mentioned, is a combination of natural convection and radiation. Okay, therefore you write this equation that you have.
So the surface area here, you didn't include the top and the bottom? It
No,
says
sir.
hanging.
No, sir. It's only the sides.
But
only the sides.
It's saying it's hanging.
Hanging, but it's hanging. It has something else means. Because this is only from vertical, showing radiation from the side. And the top, we have to go and deal it differently, sir.
Okay.
Okay. Therefore, this is by convection from the side.
Okay, thanks.
Right? Is only from the side. Now we have to look at the other two surfaces. The other two surfaces are flat, heated upside, flat, heated downside. Okay.
So we use horizontal plate for the top and bottom then?
Absolutely. Therefore, let's go back here. I'm sorry, ladies and gentlemen. Therefore, now we have these two scenarios. Upside, downside, okay? Therefore, we assume here there is inside also 40 degrees. There is no heat transfer in this direction. It means it's insulated. Therefore, this temperature surface and temperature surface given, okay? Therefore, I'm sorry, again. Therefore, we calculate it from the side. Then we go to top surface. As you mentioned, sir, you have to calculate the characteristic length. And this is horizontal. The characteristic length is defined as only as area divided by perimeter. They use it just to make sure that you have something, okay? Therefore, they use this as a definition to find the characteristic length. And then we find here. Now you have characteristic length. Now we have to go back and calculate the Grashof number, because the Grashof number is a function of the characteristic length. Before it was 0.4, now it's 0.1. We're going to calculate the Grashof number. Keep in mind, Grashof number, temperature difference, beta G, characteristic length to power 3, kinematic viscosity to power 2, and you can see this is less than 10 to power 9, okay? It multiply by Prandtl number, that we did it, therefore you find Rayleigh number directly. Then we go to table 9.1 and look at table 9.1. This is surface, top surface. Therefore, we look at that part and use this equation. It's easier because this falls exactly on the range of the first one, okay? You can use also the equation number 3. There's nothing wrong, but here you can do that, okay? And you calculate the Nusselt number. Again, we do have the Nusselt number. We do have conductivity and characteristic length. We can calculate the heat transfer coefficient. You can remember now we are talking about the disk now. We are talking about disk, therefore this is the area of the disk. If you notice, this is only we're looking at the plate on the top. The plate on the top is a circle, therefore this is the surface area. Now you have the H, you have the A, and you have the temperature difference, and you calculate this one. Any question, please?
Sir, if it said it was insulated from the top and the bottom, we don't have to do this, right?
Here it mentioned we are the question is not a little bit clear to me. What we are saying here is we are using the concept of insulation, not the completely insulated. It means the fluid inside is at 40 degrees. And the temperature here, therefore, there is no heat transfer from this one here, from the plate to here, okay? That's the concept. And here is the bottom of the plate, and inside it is a tank, and the water inside at 40 degrees. Therefore, there is no energy exchange between this plate and the fluid up there. And therefore, it means there's no energy exchange. That's the concept that we are going to use it, okay? Therefore, here we have a plate exposed to indoor environment, and the temperature of the plate is 40 degrees. Did I answer your question, sir?
I mean, if from outside, if it was insulated, then we don't have to do this, right?
It depends on the temperature of the insulation outside, okay? If you insulate it from outside, but if the temperature of the insulation is the same temperature of the room, therefore there is no temperature difference. But if you insulate it rather than 40 degrees, 30 degrees, still you have energy exchange, okay? But this insulation, the whole is a concept they're using here is there is no energy exchange between this plate and the liquid inside the tank. This insulation here is the tank is full of water at 40 degrees, therefore there is no energy exchange. But in your application, if I go and I put the insulation on the top, but it's still the temperature on the top of the insulation is 30 degrees, still I have energy exchange by natural convection. Okay, therefore we calculate here if this is the value we can find, okay? Now we go back. Now this is amount of energy exchange by convection from the top surface of the tank. We have to go back and repeat the same thing. So here, we have to repeat the same thing from the bottom plate. That's why I mentioned it's hanging, okay? That's why I added a statement hanging that you know that also the bottom is exposed to the air. If the tank is on the floor, there is no natural convection. But since there is a cylinder, the characteristic length is the same, Rayleigh number is the same. The only thing we have to look at the other formula for the bottom plate. Okay, do you agree with me? The bottom plate, again, the same characteristic length. Since the characteristic length is the same, the temperature is the same, then we end up the same Rayleigh number. But now we have to go back and check the correlation for the bottom. And if you do that one, you will see this is the correlation for the bottom plate. Okay. And just again, your engineer, look at here, from the top was 20.61. For the bottom is 10. In case your calculator make mistake, and you find this is 100, use your judgment. It has to be less because the top plate is hot. Therefore, there is less convection than on the top. Okay, the bottom you have less convection rather than the top. Okay, use your judgment as you go to the problem, and if you find the answer, just think for a second. And again, we find this one, and we calculate, and therefore we can end up that one. By convection from the side, we calculate. From the top, we calculate. From the bottom, we calculate. This becomes this value. And the same thing, we can calculate by radiation. We have the temperature of the room, the wall of the room mentioned, the surrounding is 20 degrees. And this is the total area of the top, side, and bottom. We add them up together, okay? This is the area that we have. Top and bottom are the same. This is from the side, and this is the emissivity here. And since this tank is inside the room, the shape factor is equal 1. Because whatever emitted from the plate, from the cylinder, will be absorbed by that. And that's why we don't have any shape factor here, okay? That's why we don't have any shape factor here. We have it, but that shape factor is equal 1. Any question, ladies and gentlemen? Any question? I cannot hear you, sir.
Saying no, sir.
Good. You woke up the rest of the student, okay? Oil at 15 degrees is being heated by a saturated steam at 1 atmosphere in double pipe heat exchanger. We are dealing with the oil at 15 degrees heated by saturated steam. I do not know what that means, and in a double pipe of heat exchanger temperature of 25. If the inner and outer diameter of this two pipe is 3 centimeters and 5 centimeters, and the oil enter at the mean velocity of 0.8 meter per second. Now he's giving you the inner tube may be assumed to be isothermal. That's why he mentioned is saturated steam. Therefore, he assumed this is the temperature is constant. And the other tube is well insulated. Okay, therefore we have 1 and 5. Inner one is at 100 degrees, outside well insulated. Assume fully developed. Okay, therefore we can assume now it's fully developed. The velocity profile is established. Determine the tube length required to heat the oil to indicate the temperature. I have no idea what is happening. Therefore, this is the temperature of the fluid is coming here and leaves at 25 degrees. Therefore, T in, T out. These are two tubes, one inside, one outside. Inside is 3 centimeter diameter, outside is 5 centimeter. And the oil entered between these two. And this is the velocity of the air, what oil is coming in. We would like to see what would be the length in order to temperature reach from 15 to 25. Okay, we have only a few minutes left. You do it in 1 minute, please. Read the problem, take your time, okay? Take your time trying to understand. Therefore, what I see, this is a forced convection. As I see it, this is flow inside the pipe. As I see it now, flow between two pipes. Therefore, narrow it down the subject that you. The temperature Ti is given. The temperature T exit is given. And the tube, also the temperature is given 100 degrees. We would like to calculate what would be, therefore what he mentioned is also the out tube is well insulated. It means there is no convection from the tube to environment. Okay, there is no convection, therefore that we can assume is 0. Okay. We would like to calculate the temperature of the tube needed in order that the oil temperature will increase it from 15 to 25. Take your time, I go for one other walk. As we mentioned, and this is a forced convection, the first thing we have to do, we have to calculate the Reynolds number. And since we know the inlet temperature and we know the outlet temperature, we can calculate that mean temperature, okay? Okay, therefore here is coming at 15 degrees and leaving at 25. Temperature of interior pipe is given 100 degrees and outside is insulated, okay? Therefore, if you would like to look at physical property, we can go to table A13 and we find these are the physical property. As I mentioned, the fluid passing between these two pipes, you have to calculate now the Reynolds number. you remember, this is we're talking here. Therefore, we have to find the hydraulic diameter to do that. And then this is becomes the difference between these two. Therefore, when you calculate Reynolds number, then the Reynolds number has to be based on hydraulic diameter that we have here. Okay. And then you calculate the Reynolds number, and then you find the also, in order to calculate the Nusselt number between inside here, outside here, which one it is. Therefore, you have to calculate the ratio between these two. Based on that one, and also based on the condition that you have, this one or this one, you will find the constant Nusselt number. As we go back, therefore we calculate this one. We have the surface area. I don't know. What procedure should we use? Which technique should we use? You see, the
Should we
unknown.
constant surface temperature?
But what procedure should we use? What is unknown?
The H.
What is unknown, my friend? He's asking you to calculate what? He's asking you to calculate the length. Okay? He's asking you to calculate the length. Determine the tube length. This is unknown. He wants to see what should be the length of this tube. The temperature increased between 15 and 25. I can easily calculate the energy exchange. The energy exchange is called, because I know the temperature is coming in, I know the temperature is going out. Therefore, if I say MC delta T, I can calculate the energy exchange. Am I correct?
Yes, sir.
Therefore, I know the velocity. I can calculate the area, become volume flow rate. I know density, therefore temperature coming in, temperature going out. It gave me the Q. But he's asking me about the length. How can I go and calculate the length?
Using the velocity of the.
I know the velocity. But,
yeah.
What should I do?
We need to see how much energy is being transferred.
I calculated MC delta T.
Energy is exchanged through the inner tube only. So
this is the same energy would carry, is the same energy has received from the steam. That's it. But how can I calculate the length? He's asking to calculate the length. I already calculated.
So it's the amount of energy that we give to the fluid.
Okay,
we need to see how much. Shit, forget it.
Remember, the energy got from 15 to 25 is the same amount of energy got through the convection. It means this is called HA delta T. We can calculate H because we can calculate Nusselt number. Then we have area. Area, it means diameter times length. Okay. Here is the length we can calculate. And also, remember, we are talking about the constant surface temperature, the fluid comes and so on. Therefore, we have to calculate also mean log temperature. Okay, read the question to find out what is exactly given. I know the area. If I multiply, this is the area, the opening area here. This is the opening area here. Okay. If I multiply by the velocity, it gave me the volumetric. If I multiply by rho, it gave me the density. Therefore, I can calculate the amount of the mass flow rate is going here. I know the temperature is coming in 15, leaving 25. We can calculate how much energy exchange. That's the energy exchange. But that's not the question. The question here is what is the length needed in order the temperature increase from 15 to 25. I want to see what should be this length here. Okay. But this energy exchange is energy exchange from the steam to this one, is to the convection to this fluid. Convection from here, because we assume the temperature is 100 degrees, and the temperature here is given to fluid. This temperature is constant, therefore now we can use log mean temperature, okay? To do that, first we need to calculate the convective transfer. You know, this is hydraulic diameter, and then we go back to here. We mentioned this is laminar flow, okay? Nusselt number for fully developed laminar flow in this one. That's why he mentions fully developed. We don't have to be worried. And based on the inside temperature given here, therefore we can find what value it is, this ratio, and find the value from this one, okay? Therefore, let me go back. Therefore, from here, we find this Nusselt number, let me see. And then we find this ratio, DI over DO is equal 0.6. We go back to the table and we look at inside Nusselt number because we are interested the Nusselt number within interior surface of the pipe here and the fluid, because the fluid going between these two. Therefore, this is for interior tube, okay? Therefore, we find this value because it's fully developed laminar. This number is constant, and we know the hydraulic diameter, and then we calculate the value of heat transfer coefficient. Now, the unknown here is
the rate of heat transfer.
The rate, the length of the tube. The length of the tube, Q by mass flow rate is equal to Q with convection, okay? But since the temperature is constant, we have to look at log mean temperature. I know the interior no temperature, I know the exit temperature, I know the surface temperature, therefore I can find this log mean temperature is equal to this one. Now I can write my energy balance equation. I know how much the Q in exchange, I know that one. I know H. The area I have to calculate because this is the energy exchange between the interior surface of the pipe and the fluid, okay? Therefore I can calculate from here. Q, this is the area. This is the energy we calculated by MC delta T. This is my H, and this is my delta mean. Therefore, this is the area become like this. Okay. Now I know this area for energy exchange. Area for energy exchange. Therefore, there is a length in this AS that I can calculate that one. Okay. Therefore, here there is. This is my AS we calculate. This is the length we want to calculate. And then this is the diameter inside here. Okay. Because this is the area, the tube, 3 centimeter diameter. This is the area of heat exchange with the fluid and the surface. Okay. That's why the area here is this one here. Okay. The point is the length of the tube has to be 53 meters. Okay, read the problem. Understand the physics of it. Find out the equation, what equation that you have to use, then start to plug in the number. This way you can save 20–30% of your time. Okay, because if it was asking me energy exchange rate, it was easy, mc delta T. Because I know the temperature is coming, the temperature going, I can calculate. But it's asking you to calculate the length, okay? Okay, ladies and gentlemen.
Sir, I have a question.
Yes, sir.
I'm not sure if you said this yet, but how do we know when to use the log mean temperature as temperature difference?
Oh, it's very good, easy, sir. Right here. Let me just show you, sir, one more time. One more time, sir. Very easy to, whenever mention the temperature of the surface is constant. Let me see why I cannot open my. Whenever they mention the temperature of the surface is constant, it means you have to use log mean temperature, sir.
Okay.
Okay. It was chapter 8, I believe.
Yes.
And whenever it mentioned the temperature is constant, it means like this, sir. Where is it? There's a graph right here. Whenever the temperature of the plate constant, it remain always constant, but the fluid comes with 15 degrees and slowly will increase. In this case, the temperature difference at the beginning is different from the end. Therefore, we calculate the log mean temperature in this case. Okay?
Okay.
Whenever you have a constant surface temperature. Okay?
Thank you, sir.
And no problem. Otherwise, when you have this one is easy. When you have constant heat flux, is easy because the constant heat flux, it means that your temperature of the surface is changing. Okay? This is the temperature of the fluid going on, and this is the temperature here. And both of them, the difference between them is remain also constant. Okay? In this case, you can use the delta T as usual. Okay? But when it comes to the case of constant temperature, is a different story. Okay?
Thank you, sir.
No problem. Okay, ladies and gentlemen, it was nice to have you. Work hard and hopefully everything will be okay. But the only thing, please read, take your time. Just do not plug in the number immediately. As I always mention, it was nice to see you only for one term. I don't want to see any of you for next term, okay?
Thank you, sir. Bye.
Thanks.
Pass successfully because this is enough for one term. I'm sure all of you know, but spend some time, read it carefully, understand the subject. Hopefully everything is going to be fine. Take your time, okay?
Thank you, sir.
Thank you.
Thank you. Thank you. All the best.
Sorry, sir, I know you mentioned
Thank
it,
you.
but I just want to make sure, how many pages do we get for the exam, for the cheat sheet?
How many sheet? How many what?
How many pages are we allowed for the formula sheet for the exam? I know you've mentioned it, I just want to make sure.
2 pages.
Okay, thank you.
2 pages means become 4 sides. This side, and 2 pages, okay? Therefore, 4 sides, 2 pages. Please do not put any unnecessary information. That's not acceptable. Okay, ladies and gentlemen, you have a tutorial. Run up to your tutorial, and tomorrow have another tutorial. Study hard. All the best.
I didn't have a chance to meet with you. This should be my last.
I hope so, sir. I hope so. Because as I mentioned, I don't want to see you next term because it's become boring. I already told you all of my jokes.
I don't know if this course is available next semester.
I don't think so. It's
Yeah.
only once in one period.
Because
anyway, try to pass it because I'm sure you can do well, sir.
Thank you. Okay, thank you very much. Hope we will meet later anytime because I'm not student in Concordia. I think you know. Yeah.
Yes.
So we might meet anywhere else anytime.
Anyway, study hard. All the best.
Thank you very much.